4.4 is on measures of relative position. And the first thing we're going to go over is percentiles. If you've ever taken a standardized test, you can remember a lot of times you get your results back. Let's say you scored at the 80th percentile or something like that. So, I mean, percentiles are used on lots of standardized tests. They just tell you how you did relative to everybody else that took the test. Okay. And one of the first things we need to go over talking about percentiles is how to find like the 50th percentile of a set of data, or the 30th percentile, or something like that. And so if you have a set of data, you have a big set of data, a lot of variables or x values, so let's say we have a bunch of data items, then the pth percentile is a value, say capital X, such that at least p% of the data is less than or equal to capital X, and at least 100 minus capital P % is greater than or equal to capital X. Alright, so for example, say you wanted to find the 70th percentile. So that means that at least 70, whenever you do find that number, at least 70% of the data items will be less than or equal to whatever data item you find. And then since if we find the 70th percentile, that means 30% is greater than or equal to whatever value we find. And in this definition, whatever value we find is this capital X. So it's an actual number in the set of data. Well, it may not be in the set of data, but it's a number relative to the set of data. So, for example, let's say that we wanted to find some percentile, some pth percentile of a set of data. The first thing that we need to do is arrange the data from smallest to largest. So we need to make sure this is how we find a percentile. First, arrange the data from least to greatest. So kind of like what you do for a median. Alright, And then the way that we find the location of the data item, we're going to call the location L. So the location is going to be equal to N, where N is the number of observations in the ordered data, over P, the percentile, divided by 100. Now, whenever we find that number, whatever this number is, it's either going to be a whole number or it's going to be a decimal or a fraction. So if it is a whole number, or if it is an integer, so we have two conditions. If L is an integer, then we will average the data value in the Lth location with the data value in the L plus 1 location. So, for example, if L is an integer, let's say L was 5, we would go to the 5th data item, we would take that data item and the next data item and find the average of the two. And then that would give us the Pth percentile. So if L is an integer, then you take the average of the data item in the L location and the next data item. So the average of those two. So take the average of the data item in the, I guess you could say, I use the word elf, just meaning the L location. I'll say just the L location and the next data item. So that's what we do if, when we work out this little formula, we get a whole number or an integer. If we don't get an integer, so if L is not an integer, round L up, not just round L, round L up to the next integer, or the next greatest integer. And find the data item in that location, that new Lth location. Alright, so the example, one of the examples in the book says to find the 50th percentile for the following set of data, or the following data set. So they give 3, 5, 0, 1, 9, 2, 7. So of course we need to first order this from least to greatest. 0, 1, 2, 3, 5, 7, 9. Now, if we want to find the 50th percentile, the location of that is going to be equal to n times p over 100. So the location of that percentile is going to be 7, because that's how many data items we have, times 50 over 100. Alright, so that's going to be 7 times 50 over 100 is 0.5, so that gives you 3.5. So that's not an integer, right? So we would need to round L up. So then L would become 4. Now go back to your ordered set of data and go to the 4th data item starting from the bottom. So we got 1, 2, 3, and then this right here, that's our 4th data item. So the 50th percentile is going to be 3. The 50th percentile is also the median. That's no coincidence. It says, given the following data, find the weight that represents the 26th percentile. You may see that written as P sub 26, like that. That's another way to write the 26th percentile. So first we need to calculate, or our data is already, no it's not. Oh, I thought it was sorted. Would have been nice if it would have been, but it's not. Alright, so I have to sort this real quick. Being a relative term. So we have 5.6, 5.7, 5.8, 6.0, 6.1, 6.5, 6.8, 7.5, 3 8.6s, so 8.6, 8.6, 8.6, 8.9, 9.1, 9.2, and 9.2. So let's count and make sure I have the same number. Alright, so there are 15 here, 15 there. Alright, so let's calculate L, the location of the 26th percentile. That's going to be N, the number of data items, it's 12, times 26 over 100. Yeah, it's 15, sorry, not 12. I don't know why I said 12. 3 times 5, I guess I said 3 times 4. Alright, so 26 times 15 divided by 100. We get 3.9. So we want to round that up always. Even if it was 3.1, we'd round it up. So we round that up to the nearest integer. So it's going to be the nearest greatest integer. That's going to be 4. Alright, so go to the fourth data item. 1, 2, 3, 4. We have our percentile. So 6.0 is our percentile. Alright. So I guess what would take the longest really is sorting the data. So if the data is sorted, it's not too bad. Let's see if I can find really quick a bigger data set that's already been sorted. Alright, here's one here. And this is straight out of your ebook as well. I'm around page 143, somewhere around there. 142. Alright, so here's some ordered test scores. Again, this table is provided in your book. Let's find the 10th percentile. So if we want to find the 10th percentile, L equals, this is 40 data items. So this is 40 times 10 over 100. Alright, and that gives us 4.0. So this is a case where we got an integer. 4.0 or just 4. So it's not where we round up. This is the other time, the way we haven't done a problem yet. So the way that we get the percentile is we find the average of the 4th and 5th data items. So you can see how these are sorted down like this, right? So 1, 2, 3, 4, 5. So we want to find the average of those two. So 27 plus 29 divided by 2. And that's going to be the 10th percentile. So that would be 28. Even though that data item is not there, you know, that is our 10th percentile. Let's do the same thing, except let's find the 88th percentile. So the 88th percentile would be 40 times 88 over 100. All right, so that's 35.2. So what do I need to do? Do I need to take 35 or 36? 36. Round up to the nearest, to the greatest integer. All right. So let's find the 36th value. If there's 10 in a column, this is the 30th. 31, 32, 33, 34, 35, 36. So the 88th percentile is 73, the 36th term. Now, if you want to take a data item, so like if I want to take, say, 50, and I want to know what percentile is that located at, so I want to find the percentile of a data item. Then the way that we do that, let's say we want to find the percentile of x, where x is, some data value. That's going to be equal to the number of data values less than or equal to x divided by the total number of data values times 100. So it doesn't have to be an actual data item. It can just be any data value, even if the value is not present in the set of data. Okay, so let's say that we wanted to know the percentile for a score of 50. Relative to the table that we have. The same table from the book. So we would need to count the number of data items less than or equal to 50. So we don't have 50, so we don't have to worry about equal to. So we just count the number of data items less than. So there's 8 in this column, and then there's 10 in this column. So that's 18 data items that are less than 50. Okay? So that's going to be our numerator over the total number of data items or data values. There was 40 in that table times 100. Alright, so let's see what we get. Alright, so I got 45. So what that means is a score of 50 would correspond to the 45th percentile. So that means there are 45% of the data items less than 50, 55% of the data items greater than 50. Alright, so we found the 50th percentile a few times. The percentile's 25, so the 25th percentile has another name. It can be called the 25th percentile, but it can also be called the first quartile. And the first quartile is abbreviated Q sub 1. That would mean the first quartile. The second quartile, then, you would imagine, would be the 50th percentile. And that's right, the 50th percentile is equal to the second quartile which is equal to Q sub 2. So what do you think Q sub 3 would be equal to? Yeah, Q sub 3 is the 75th percentile. Or the third quartile. So whatever the subscript number is. And so what does that really stand for? Well, if you find the first quartile, then 25% of the data items will be out or below that data item or that value, and 75% will be at or above that value. If you find the second quartile, the median, then 50% is equal to or below, 50% is equal to or above. Third quartile, that would be the 75th percentile, so 75% is equal to or less than the third quartile, and 25% is greater than or equal to the third quartile. Another term sometimes that you'll see used is the interquartile range. And the interquartile range describes the range of the middle 50% of the data. So think about what that means, the middle 50%. So 50%, if you think of 50%, it's like right at the middle if you're thinking about like a percentile. But what would the middle 50% be of the data items? Well, if you could figure out the first quartile and you could figure out the third quartile, so you figured out the 25th percentile and you figured out the 75th percentile, 75 minus 25 is 50. So that's how you find the interquartile range. You say the third quartile minus the first quartile. So remember, the third quartile is like the 75th percentile, And the first quartile, that's like the 25th percentile. So if you take that difference, you're getting the middle 50% of the data, the range of the middle 50% of the data. Now, that may not sound important, but whenever you start analyzing sets of data, then that is important. One way that quartiles can be used is in the construction of box plots. If you have a graphing calculator, or you know how to use Microsoft Excel really good, you can do box plots. Box plots are just a graphical summary of the data which look like a box, believe it or not. So a graphical summary of the central tendency, the spread, the skewness, and the potential existence of outliers in the data. So we get a lot of good information from a box plot. I mean, it is just a graphical summary, but depending on the location of the boxes, whenever you do your plot or your graph, it can tell you how the data is spread out, if it's skewed to the left or right, and maybe if there is outliers in the set of data. We've used the word outlier a few times. We said that the mean was greatly affected by outliers. A trimmed mean would not be as affected by outliers. What is an outlier? I mean, I think we kind of know what it is just thinking about it, but the way that an outlier is defined in your text is it says a data point is considered an outlier if it is 1.5 times the interquartile range above the 75th percentile, or 1.5 times the interquartile range below the 25th percentile. So you have to keep in mind what the interquartile range is. You have to be able to find that in order to figure out if a data item is an outlier. So remember, the interquartile range is Q sub 3, or the third quartile minus the first quartile. So if you take that, say it times 1.5, if a data item or a data value is that much above the 75th percentile, or that much below the 25th percentile, then it is an outlier. All right. Let's see if I can find this figure in your ebook real quick. Just 1 second. This is around page 144 of your ebook. If you want to know what a box plot looks like. So this box plot was made from the data that we were just working with in this table here. Let's see, right here. So if we figured out the first quartile or the 25th percentile, we figured out the 75th percentile or third quartile, this is what a box plot looks like. So you see this right here, this is Q sub 1, the 25th percentile. This is Q sub 3, the 75th percentile. And then this right here, right in the middle, that's Q sub 2, the 50th percentile. And the line goes from the smallest data value to the largest data value. And then you just create a box here, just like that. It's just another way to represent data, and you can kind of see where the quartiles fall between. And you could even, if we knew these exact values, we could calculate the interquartile range, say Q sub 3 minus Q sub 1. Not very easy to, I mean, it's not very hard to figure out. And then we could figure out outliers. If we know the interquartile range, we say that times 1.5, right? And then we could figure out what a data item would have to be an outlier. Alright, so for example, I believe your book figures out that, let's see what if it figured out the interquartile range. It says the 25th percentile, which the easiest way to write that is just Q sub 1, was equal to 18. And then Q sub 3, the 75th percentile, was equal to 82. So you could figure out the interquartile range That can't be right.
It's 42 and 65.
Yeah, sorry. It's 42. I think I was looking at another set of data. And what now?
65.
65. All right. So then, what would the interquartile range be? 65 minus 42. So 23. So then if you said, if that's the numbers, I'm still looking. I'm sure those are probably right. Yeah, I see it now. So it says that 23, this is 23 units here, from here to here. All right. And so if you want to know if a number is an outlier, say 23 times 1.5 all right, that gives me 34.5. So if you add 34.5 to 65, so that's 99.5. And then if you subtract 34.5 from 42, you get 7.5. And so if any data item is less than or equal to 7.5, greater than or equal to 99.5, then it would be considered to be an outlier. So that's how you can use the interquartile range to tell if you have any outliers in the set of data. It's not too bad. As long as you look at the right set of data, it's not too bad. Another very important term, and something that we're actually going to use a lot in here, we may not use it very much right now, but we will use a lot, is called a Z-score. And what a Z-score does is it transforms a data value into a number of standard deviations that value is away from the mean. So the Z-score transforms a data value into the number of standard deviations the data value is from the mean. And so it kind of, it's like it standardizes a number in a way so that we can tell its relative position. We could use the Z-score to do all kinds of things, but one way would be, you know, if you wanted to figure out, say you had a male that was 7 feet tall and you had a female that was 6 feet 8 inches tall, and you wanted to know relatively who is taller. Well, we would have to know some data about males and females, but you could figure out relatively who was taller. So, and that's just one of many applications that we could use to, or ways that we could use the Z-score. We can also use the Z-score to help us figure out probabilities. If we know certain data values, like the probability that if I randomly selected 5 males, their average weight would be greater than 170 pounds. We can use you know, standard deviations and Z-scores and all that kind of good stuff. We can use that to figure things like that out using probabilities. The formula that we use to find a Z-score is Z equals X, the data item, minus, and this depends on whether it's a sample mean or population mean, but if it's a population mean, you'd use mu divided by, and again this depends on whether it's a sample or a population standard deviation, but if it's a population standard deviation, you'd use sigma. So the Z-score is equal to X minus mu over sigma. When you calculate the Z-score, that's going to tell you how many standard deviations away from the mean that X is equal to. Okay, so it's a real easy calculation, and that calculation is always rounded to 2 places because we use a table a lot of times with our Z-scores, and that table only goes to 2 decimal places. Alright, let's look at this example real quick. This comes straight out of the book as well. Alright, so suppose that you scored an 86 on your biology test and a 94 on your psychology test. The mean and standard deviations of the 2 tests are given below. So let's figure out the Z-scores of the 2 tests. Alright, so let's first do the Z-score for the biology. So Z equals X minus mu over sigma. And then we're going to round to 2 decimal places. So it said that we made an 86 on the biology test. So 86 minus the mean on the biology test is 74 divided by the standard deviation is 10. Okay? So that would be 12 divided by 10, or 1.20. Alright, let's do the same for the psychology test. It says we made a 94. So Z equals 94 minus the average, or not the average, minus the mean, 82, divided by 11. Alright, if we round this to 2 decimal places, I get 1.09. So what that means is, on the biology test, we scored 1.2 standard deviations above the mean. And on the psychology test, we scored 1.09 standard deviations above the mean. So even though the score on the psychology test was greater than the score on the biology test, relatively, we scored better on the biology test than we did the psychology test, relative to everyone else that took the test. Okay? All right, and that ends section 4.4.